It stands for Hodge star. Yeah, and I don't know, is that recursive? I guess so. But in any event, the basic chain here to remember is that D increases the dimensionality of the object that you're working on, right? So if you had one number per vertex, then D is like a derivative, and subtracts gives you one number per edge. For one number per edge, you apply D again, then you get one number per triangle. And on a tetrahedral mesh, like what we see here, you can do it a third time and end up inside of the tets. Right? And then the star operator was the thing that flipped from k forms to n minus k forms. Yeah? And so for instance, it like multiplies, divides by area, and so on. And really the key topological property that we're going to use today is that d squared equals 0. Yeah? And this is really the beginning of a lot of different topological theories, is defining some operator that looks like a d. Sometimes it looks like a d, sometimes it looks like the delta, sometimes it looks like a partial derivative d, and then showing that when it's square equals 0, then there's a lot of cool things you can say about math. That's my high-level story, and you can ask Ed for details. But in any event, in our case, we've built up what you might call a discrete de Rham complex. Essentially, when you hear the phrase de Rham cohomology, you can now use that at bars to, impress your friends. Essentially, it just refers to this set of k forms from 0 to n, where n is the dimension of your manifold, equipped with these derivative and star operators, right? And as a tiny bit of review, additionally, of course, if you want the cotangent Laplacian operator in this discrete de Rham complex, how do you get it? Isn't it cool you can parse phrases like that now? This is a fun class for vocabulary words. So the Laplacian operator is essentially what you get by taking loops in this complex, right? So if I want the zero form Laplacian, which is the thing that acts on functions, I can get it by doing, let's see here, star d, oops, I already got it wrong. D star, right? And that takes me from zero forms to zero forms, so that's a reasonable operator. Right? And that thing has eigenfunctions, which are exactly the ones that we've already talked about in this class. Yeah? And in fact, this allows us to define higher order Laplacian operators, and in just a minute we'll talk about what those do. And the answer is not very much. Okay. So in practice, what do? We build up this like hella matrices here, right? With all these different Ds and stars and things, and you just have this in some piece of code that you don't look at, and then from there, you can do all kinds of cool geometric PDE on a triangulated surface, yeah? And so we talked about a few, and in particular, there's our Laplace operator. Okay, so this is where we left off. Yeah, was talking about the Helmholtz-Hodge decomposition. Just out of curiosity, how many of you guys have seen something that looks like this in some form or another, where you take a vector field, I think usually in calculus class you see it on the plane, right? And you decompose it into the sum of two things, right? A divergence-free piece and a curl-free piece. Yeah, so just out of curiosity. It used to be in calculus class that we learned this, but I think it's kind of a lost thing. But it turns out that this theory lifts to manifolds, and it really is kind of a topological statement about k-forms. Probably your instructor didn't use that phrase when they talked about it in calculus class. But the basic idea here, remember that I have, if I ignore the primal dual structure for a minute, yeah, then I have this sort of chain of operators, right, that goes from 0 forms to 1 forms to 2 forms, and so on, and I have this D thing. Right, and remember that this is kind of overloaded notation. The D operator takes me from k forms to k plus 1 forms. Yep. And D squared equals 0. Then the question is, how can I understand the space, for example, of 1 forms? Well, okay, so you might not have seen the Hodge decomposition in your calculus class, but how many of us remember the rank nullity theorem? Not everybody, you're killing me. So remember that if I have a matrix A, yeah, and A is in R to the m by n. Yep. So in particular, maybe I have all of Rm. There's Rm, right? And then I could look at the image of A, right? Remember that the image of A is equal to what? It's equal to the set of all where x is in Rn. Yeah? Just all the things that can come out of A. Then like sort of geometrically, what is that? That's like some plane. If you're wondering, that plane goes through the origin. It's some plane through the origin, which is the image of A. And it might be all of Rm, it might be something less. It's just some space. Yeah? So essentially, the Hodge decomposition is something quite similar. The idea is that I have this D operator here. So I could take the set of all 1 forms and I could ask, what are the 1 forms which are D of a 0 form? Yeah? And that's some subspace sitting inside of here. Does that make sense? So first of all, what is that subspace? So let's think physically for a minute. Remember that D, in the particular case of 0 form to 1 form, is like gradient. So they're like all of the functions that are the gradient of something, right? Which is the thing we remember from physics class, right? That's like the, conservative vector fields, I think? Yeah, right, exactly. So if you differentiate the voltage, then you get what? Current, magnetic field. I don't know, I'm sorry, my E&M is really bad. You get some damn thing which corresponds to things that don't look like magnetic fields, right? They look like electric fields with dipoles and things. Okay, right, so you have the image of D, and then you have the whole space that's orthogonal to that, and that includes vector fields like this, right? Because that can't be the gradient of something, right? Because gradient tells me to go downhill. If I could walk in a circle and keep going downhill, I'd be in trouble. Yeah? But remember that I actually have an operator going this way as well. That's this delta thing. What is delta? Does anybody remember the definition? Star D star, yeah? In case you're not sick and tired of this from your homework, you'll be doing lots of like D star, D star, D star, D star, you know. Luckily there's only like 2 operators. I guess there's a wedge too. We don't emphasize that here because actually discrete wedge is a tricky thing to define. Right, so that corresponds, remember that star rotates by 90 degrees, yeah, in 2D at least. We'll take a look at this vector field, which conveniently, in a recent paper submission, we called this a sun-shaped singularity, and for some reason our reviewers really didn't like it. But in any event, let's say that I have this sun, see it's shining, I don't see why this is like unreasonable, yeah? And I take all of these vectors and I just rotate them 90 degrees. What do I get? I get something that circulates. Yeah, so somehow star converts suns to tornadoes, and you know, because the flow of this thing looks like that. Yeah, and in fact, remember the delta here, right? That's equal to star d star, right? And so really, what's hiding here, and remember that on a surface, 2 forms and 0 forms are kind of the same up to the star. Remember, because they're complement of each other. So in fact, what that corresponds to are these divergence-free fields. And there's an additional fact which we're going to prove discretely. We're not going to do it in the smooth case because I'm bad at math. And that's that these 2 things have to be orthogonal to one another. In other words, if you take the inner product of a curl-free field and a divergence-free field, you get 0, and that's going to be super useful. Okay? Yes, Colton.
Is this only for 2D manifold?
That's a good question. This picture that I drew here is sort of 2D specific, right? Because if I had a volume manifold and I had that star, I somehow couldn't draw exactly this thing anymore, because now 2 forms and 1 forms are dual to one another. So you're right, the picture is a little bit different. On your homework, you'll actually work out some of the details of that, I believe. Yeah. But it's a reasonable kind of schematic to draw. And certainly this decomposition we're going to derive works in any dimension. Yeah? Okay. So what I claim is that I can take any 1 form, remember that's secretly just a vector field, and decompose it as a sum of 3 things. D of something, delta of something, and a 3rd thing. Okay? But these 3 things are going to have some nice properties. Okay, so first of all, let's derive a quick result about sort of D and delta combined together. So let's say that I have, remember that the inner product of 2 primal 1 forms? You remember how this works on a mesh? Can I take one guy, then I put the Hodge star, and then I have the other guy? Yep. So let's say that I have, I want to take 1 forms that specifically have this interesting form. So I'm going to say that one of my 1 forms kind of comes from going this way in my complex, and the other one comes from going that way. Does that make sense? My question is, what is their inner product? What's your guess? 0. I mean, like, in some sense, just because I asked you to guess, like, what other number would it be? And you'd be right. Okay, so let's expand this expression, because this is a little bit, this is hiding like a lot of stuff. Yeah. So first of all, remember that delta is secretly star D star, and I'm writing a bunch of space in between them for a reason. I recommend you do the same in your notes. And there's a beta. And then the inner product of one forms requires another star here, right? Because that's the thing. Remember that star is the thing that flips you from primal to dual. It's like multiplying by the area of a cell. Yeah. So it kind of makes sense when you take dot product, you need like DA. Yeah. These are, so I'm thinking of these like matrices. So this is truly a transpose. Yeah. Good question. And then we have D alpha. Okay. And so let's reverse engineer this expression a little bit and add some detail here. So first of all, I want these to be primal 1 forms. So I know that there's a primal 1 here, right? And so let's engineer this a little bit. So first of all, in that case, what does the star operator do? He goes from primal 1 to dual 1. By the way, on your homework, I recommend you be this explicit. It really helps if you're not used to this kind of stuff. Okay? That means that the output of this D is a primal 1, right? Which means that this is like that. Does that make sense? So this is from 0, in fact, let's be super explicit, to 1 forms, and it is in the primal. Okay? Cool. And that means that alpha, by the way, is a primal 0 form. This is, by the way, a good way to just kind of type check when you're doing your math. You can kind of work through and make sure that all of your things live in the right space. Okay? Similarly, this whole thing needs to be a primal 1 form by the time it gets here, right? So let's reverse engineer this thing. So clearly, this has got to be dual 1 to primal 1. Yeah? This is going to be what? 0, 1 dual. Yeah? This is going to be primal 2 to dual 0. Yeah? And this is a primal 2 form. Does that make sense? All I did is just kind of fill in everything I need in this expression to be able to parse precisely what all these objects are. By the way, if you took exterior calculus in like the math department where we are here, none of this extra notation is needed, right? Because all these are just operators, and somehow distinguishing primal and dual is irrelevant. Yeah? Okay. Let me type check that with my notes really quick, because if I made a mistake here, we're host. Primal tools. Yeah, okay, good. All right, so let's remember that transpose of a product is the same as product of transposes flipped backward. Yeah, so let's do that. Okay, so what do we get? Well, we get beta transpose. Somehow the type of beta doesn't matter here because it's just a generic object. Yeah. Okay, what is the transpose of the star matrix? Remember, the star is just diagonal. It's a star, yeah. So this is a star primal tool 2 to dual 0. Okay. Now, right. So first of all, D01 dual, I claim is the same as D1 2 primal transpose. We showed that last time, yeah? Remember the D matrices are just transposed of each other depending on whether you're in the primal or the dual. And sort of this is the right dimensionality if you work it out. So in other words, this is D1 to primal. I'm doing that for a reason. And then finally, we have this thing, which again is equal to its transpose. Notice a really sneaky thing happen. You know, I did this for a reason, which is, notice we go dual 1 to primal 1. This guy inputs primal 1 forms, right? That's why I thought I'd make that little argument here. And now this whole expression parses again. Okay, now we have this star primal 1 to dual 1. Okay, and then we have D01 primal alpha. Okay, first of all, what's the product of these two things? I just say identity. Yeah, these are just inverses of each other. Okay? So these guys go away. And what am I left with? I'm left with D01 times D12. What is that? Oh, it's D squared. You're killing me. I literally, the answer to every question I ask in this class is the same. 0. Yeah, so this thing is 0. Okay? So what does that tell me? That tells me, remember that like this is fancy notation, but these are just matrices. Yeah? So this D and delta are just matrices. And so the schematic picture that you should have in mind, right, is that here's some space. Believe it or not, this is R to the mod E. Right? This is all one number per edge. And it decomposes in a sort of orthogonal way, right? That there's like the image of delta, there's the image of D. What we just showed is that those two things are orthogonal to one another. And then there's other stuff. It's a technical term. Actually, the technical term is harmonic. Okay? Right, and by dimension counting, one thing you can convince yourself, what do you think the dimension of this thing's going to be? If you're really good, you can get it from the de Rham cohomology, or you can just say like, well, there's only like two answers, 0 or the other thing, which is like Euler characteristic, yeah? There's like only so many integers that show up in this area. Yeah, so this, the dimensionality here just has to do with the number of holes, okay? And really the schematic is this, that the D vector fields are the ones that are gradients of things, the star D star things are circulatory, and what's left are harmonic stuff, which go around the outside. Yeah, so what do you think the dimensionality of these things is for planar vector fields? 0, right? Because there is no such thing as going around the outside. Yeah, and in fact, you can check that works out. If you triangulate a disk, if you do your dimension counting here, you'll see that what's left when you do this orthogonal decomposition is nothing. That's it. Okay. Cool. So right. So what did we just show? We showed that we didn't quite show what's on the screen here. We showed something close. Right. So we showed that I can take an omega and I can decompose it as d beta plus d alpha plus gamma. But what we've shown so far is that gamma is orthogonal to the image of these two matrices. And I claim that's equivalent to the two conditions that I've written in this orange box here. So in particular, you know, these boards are like topologically really a problem. This thing is useless, right? Because if I want the other one to go up, then, okay. The math department too, you know? I actually don't know. Those of you who do computational design, is there like a way to design boards so that they never get, you know, they're always useful? I think if you had a third row, then you'd be okay. You could just keep permuting. Okay, right. So, right. So remember that gamma here, by definition, now we're just applying the rank nullity theorem, right? So the rank nullity theorem says I can take anything and write it as the image coming out of a matrix plus something orthogonal to the image. Yeah. So what does gamma being orthogonal to the image of delta mean? Well, in particular, remember that means that, so what is going on here? So if we go back to our expression here, right, notice the image of delta is everything to the left of that D01, right? That's the only part that came on the other side of our inner product. So really, what does that show me? That shows me that star D, yeah, that's what that tells you if you read off of that expression. Now I'm being sloppy about my dimensions because I'm tired of this. Okay, but remember star is an invertible matrix, so really this is the same as, which is the condition that we wanted. Yeah, and similarly, right, so gamma is also orthogonal to the image of D. Right? So you have to be careful. Remember that means that D transpose star gamma equals 0. Right? Because that's what it means to be orthogonal. You always have to take dot products with respect to this star operator. Yeah? And I can stick whatever invertible matrix I want in front of here and nothing changes. Yeah? So if I put star here, then you end up with delta, and that finishes our little proof here. Yeah? So this is like yet another case where the discrete is way easier than the smooth math, right? In order to show that a discrete Hodge decomposition exists, it's just basically linear algebra, right? This is fancy notation, but really these D's and deltas and stars and things are just matrices, and we're just applying stuff that you knew from algebra class. In order to show this in the smooth case, you'd have to go to a heck of a lot more work. Yeah? So it's kind of a nice thing. So this is actually a useful decomposition in practice. There's a lot of times when processing scalars is a heck of a lot easier than processing vectors. In fact, actually, just the other day, we had some physicists in my office that wanted to compute curl-free fields for some reason that I'm not totally sure about, and of course, they were using some Hodge decomposition stuff. one question you might ask is, if you give me a vector field, can I give you the Hodge decomposition? Which is really a linear algebra question. Obviously, from the way that I've written it here, I could set up a linear system of equations to recover it. But there's actually a slicker way to do this. Does anybody have any ideas how I might recover Hodge decomposition? So in other words, you give me omega, and I want to give you alpha, beta, and gamma. What could I do? Like, in some sense, there's only so many sledgehammers we have. In fact, I can think of two, D and star. Yeah, so what happened? A fabulous idea. So what am I going to do? So D of omega.
The second and third term dot, right? Because D squared dot.
You got it. And what is D delta?
D star will apply.
Yeah. Yeah? Slick, huh? And similarly, what do you think delta of omega is? Yeah. Right? So these are just Poisson equations. We already talked about how to solve these in this class, right? So this is a way to do it. And then how do you get gamma? Yeah, it's just whatever. Yeah, it's just a way you just take the remainder and you're done. Yep. This is a slick algorithm for doing this in 3 steps. And yeah, that's all it depends on. Any questions? Kind of cool. So this is a nice, like, very self-contained application of this discrete exterior calculus business. And it's really the beginning of a lot of stuff, right? So in vector field design, this is a useful tool because it gives you a nice way to think about fields and their sort of topological pieces. Yeah? Okay, one reasonable question you might ask. So we define this Hodge Laplacian to be sort of all the different ways that you could start at a K form and end up back at the K form. Right? So that's D star plus star D star D. And you could ask, like, well, what is this thing for higher dimensions? The answer is a little bit hard to think about geometrically. So this object is called Hodge Laplacian. It doesn't necessarily measure smoothness in the fashion that we think about. In fact, my undergraduate thesis was on a different operator called the killing form, which probably actually is closer to what we intuit when we think about smoothness of field. But it does measure some kind of derivative. And in particular, you could ask, what are the eigenfunctions of this one-form Laplacian operators? In other words, like kind of harmonic vector fields. Well, now, we only have one hammer. We might as well hit some nails with it. So if I have an eigenfield of the Laplace operator, that thing has a Hodge decomposition. Yeah? So I can plug this thing in and ask, what expressions do I get for alpha, beta, and gamma when I do that? Yep. So in particular, right, if I have, this is my basic expression, right, that Laplace of omega equals lambda omega. Let's say these are one forms on a surface. So on the left-hand side, I just plugged in Hodge decomposition. Looks like I already screwed up the sign, but whatever. We know in this class that's kind of arbitrary. Okay, on the right-hand side, well, what is Laplacian? Well, there's the definition. And here I plugged in the expansion of omega again. Yeah? And now what do I do? I just push all this stuff through, right? And I get these crazy expressions like star D, star D, star D, star D, and so on. But essentially, what matters here at the end of the day is what? Remember that this is an orthogonal decomposition. Yeah? And so one thing that you can convince yourself, well, notice that this object is D of something. Yeah? There's D star D star D star D, right? But in particular, if I factor it like that, then I know that this thing is secretly curl-free. Yeah? Because there's a D in front of it. And similarly, well, look, there's a star D star sitting in front of this guy. So he is secretly the other guy, divergence-free. Yeah? So in other words, I can set this expression equal to the first one, this expression equal to the second, and solve. And what does that imply? It implies a really disappointing fact, which is that eigenfields of the Hodge Laplacian, all they are eigenfunctions of the scalar Laplacian, just differentiated and or rotated from each other. Yeah. So it's actually, it's either depressing or really useful depending on how you think about it, right? If you want a basis for vector fields on a surface, you can get it by taking a basis for functions on a surface and just differentiating it and applying star. Yeah. Cool. So there's all kinds of fun reasons why you might need this kind of stuff. There's actually a whole, I thought this was kind of funny. There's a whole survey on applications of Hodge decomposition. I mean, this thing dates back to what, the 1700s, I think. But there's now a survey from the IEEE on how to use Hodge decomposition in your everyday life. And they have this really neat little timeline that tells you, based on communities like books, graphics, physics, math, vision, imaging, and astrophysics, all of the places where they find the Hodge decomposition and their sort of family tree. I think it's really interesting there are isolated nodes here, which I guess correspond to like somebody inventing it again. But in any event, you should page through it because there are some kind of neat things you can do. So some simple things include, you take, maybe you want to find the eye of a hurricane as I think the most obvious application of this stuff, right? Because the eye of a hurricane is really the center of the divergence-free piece. In fluid simulation, you might not have realized it, but I know that a few students in this class have implemented fluid simulation tools, and they actually implicitly were using the Hodge decomposition, whether they called it that or not. Because of this step they call pressure projection or divergence-free projection in fluids, where remember that your typical fluid doesn't compress, at least if it's water. Right? So the velocity field of the motion of the fluid has no divergence, because if it did, it would smash, it would be like a balloon. And so a very typical step in a fluid simulation algorithm is you have Navier-Stokes, you time step it forward, but because Navier-Stokes is a hard equation to solve, pretty soon your velocity field has a bunch of divergence in it that you didn't want. And so what do? You actually do exactly what we just proved on the board here. Notice this Laplace operator. This is exactly the one you invert in the pressure projection step of a fluid simulator. It shows up in other places. So for instance, one of the early applications in geometry processing is people kind of propose this stuff for I'm designing, this is kind of a strange example. I'm like putting hair on somebody's ear. This is a problem in my everyday life, and maybe I want to reduce I want it to be more or less curly. I can do that by editing the vector field different ways. It shows up in turbulence, optics, all kinds of fun stuff, and of course these days in machine learning. So if you have, there are some cases where you actually get vector field valued data is not terribly uncommon. So for instance, maybe I have buoys that are sitting in the ocean and they're collecting where the wind is going, and this is some sparse, noisy sensor that I'd like to infer weather patterns from. Then a very reasonable way to kind of stabilize that measurement would be, say, rather than to compute the vector field, sort of the relevant aspect of the field in some senses is topology, right? It's like where it's cycling around and so on, right? So maybe a bad output of one of these inference techniques is a vector field with lots of little eddies in it, in which case using the Hodge decomposition pretty directly is a nice thing to do. If you guys are looking for fun, do you still have a reading assignment left? I think you do. No? Well, if you did, then a fun paper to read that came out about 2 years ago was by my friend Fernando de Goes. So one thing that we cover in some detail in our undergraduate graphics class is this idea of a subdivision surface, right? So for those of you who aren't familiar, the idea here is like this mesh is not terribly useful as a computer graphics object. It's very coarse, right? And so Catmull and Clark and all our friends in the 1980s computer graphics world defined these rules for taking a triangulated surface and kind of subdividing all the triangles to make it smoother. And this is kind of a really fascinating paper where what they propose is like, I would like to do exterior calculus on this guy because my computation is easier. He's a coarse object. But I'd really like if my exterior calculus were somehow capturing the nice structure from this smoother thing, right? And so what they do is they sort of subdivide a few times, compute those D and star operators, and then like pull them back here. And they show that they get sort of better behaved objects because they're sort of secretly working in this smooth object just in a reduced space of functions. So for instance here, remember in our very second lecture, we actually secretly used this machinery to talk about harmonic map, like to parameterize surface, right? Now we know that secretly we were solving star d of a function equals 0 to parameterize, subject to boundary constraints. And the kind of interesting thing that happens here is that like this is what we covered. So what they did is they took a checkerboard in the plane and lifted it to the surface as the texture map. That by using this subdivision tool, you actually get things that sort of respect the geometry a little better. This is an interesting interface between discrete and smooth stuff, right? Like somehow, if you buy into the dogma, you should be able to just do it on the left-hand side, but that didn't happen. Yeah? Just recently, my colleague Amir Vaxman has an extension of this paper to do other kind of vector field processing topological stuff that's sitting on archive. Now, those of you who are math students might ask a slightly different question, which is, we just spent all this time defining and manipulating anti-symmetric K-forms on a surface. Yeah, and this begs a certain question, right? Which is like, okay, well, I cut out half of the space, right? I cut out all these symmetric K-forms, and those are really important. Can anybody name a symmetric form on a surface? Remember that anti-symmetric form is one where I swap the inputs and the sign changes? What's an example of a symmetric one? Oh, you don't count. Just kidding. Yeah, the math student. The metric, right? Dot product. Yeah, dot product, I swap the inputs and the value stays the same. That would not be an anti-symmetric K-form. And there's a totally reasonable question, which is, can I take all this cool deck stuff and make it work for exterior for symmetric forms as well? The answer is we don't know. So there's a paper a couple years ago at the Symposium on Geometry Processing, which shows how to do this. I love you. By the way, this Derivation name shows up a lot in this area. He's a nice guy. However, I would argue that the title of this paper is a little misleading. So this theory only really carries through for flat surfaces. In other words, like planar things. And in fact, to my knowledge, there doesn't really exist a nice analog of all this theory when you have a curved object. So if you're looking for a really good, challenging, discrete, smooth math kind of problem, there's one hiding here. Okay, so to summarize from like, gosh, Ed's lecture 4 lectures ago all the way till now, remember we left this missing piece in our big table of different ways to represent fields. There was like per triangle, per vertex, and per edge. Now you guys have seen the per edge representation, and you can see that there's a lot of pros, right? Somehow it's coordinate free. There's some kind of slick interpretation and certain structures preserved from a cohomology. On the other hand, this Whitney basis, in other words, like if I wanted to go from a one form back to the field itself, it's actually discontinuous along edges, which is a little weird. And sort of there's sort of deformation issues that can come up. Right? This is really good for tangent fields, not so good if you care about extrinsic stuff. Okay, and with that, I can wipe the sweat off of my forehead and go back to topics I actually know about. So let's talk about segmentation and clustering for something completely different. By the way, it's not completely different. The way that this class is organized, just to remind you guys, remember that we kind of started with a magnifying glass held up to one surface, and we talked about curvature, right? And then we stepped back a little bit. We talked about the Laplace operator. Now we're going to step back a little bit further and talk about entire regions on a surface. So rather than taking derivatives of functions, now we're going to do things like segmentation, which requires summarizing information over like a finite patch. Yeah? And then after that, we're going to talk about correspondence, which takes two surfaces and maps them to each other. And then we're going to end this class by talking about shape collections, right? Like a whole, I have everybody's brain in this classroom at once, and I want to put them all in correspondence kind of thing. Yeah? One thing you'll notice from here on out is that this class will become more and more heuristic. I think this is about the interface where the sort of cool discrete exterior calculus, finite element kind of people have kind of reached. You might notice that the dates on the papers I was just showing you are like the last 2 years, right? So I think these areas are ripe for some more kind of careful consideration in this sort of language. And there's probably some nice things to be done. Okay, so now, in some sense, we're going to step back 20 years. I think clustering segmentation problems have been around just about forever. And are really some of the basic stuff that you've probably encountered in a machine learning course if you've taken it, right? So in learning, we call this what? Unsupervised learning. But indeed, many of these topics predate learning and really actually go back to geometry community. The first question you should ask is, what is the difference between clustering and segmentation? I would argue there really isn't one. I found this puzzling quote in somebody's blog that explicitly addresses what the difference is. Apparently in like business speak, these are, like I have a customer base and there's like, I want to segment my customer base, or I want to cluster it, and these are slightly different things, but I read this sentence like 8 times and I couldn't figure out what it was saying. So if you guys have a good explanation, I'd be curious to hear. But from my perspective, really our goal here is to take some geometric objects and divide it into pieces. I think that's a much better defined task. And there are many applications of this kind of thing. So I think one of the earliest applications was in medical imaging, where really, like if you look at a 3D model of the brain, there's a lot of people who have sort of developed theory that involves, certain folds are involved with different functions and interact with each other in different ways. And so the segmentation problem there makes a lot of sense. In computer-aided design, often you want to segment a surface into patches that are somehow amenable to like putting nice smooth things on. So like here maybe I have a mesh of this object and I really would like to approximate it with like a CAD model. And so I want to identify kind of CAD model looking segments on a surface. Anybody know what this 3D model is called? It's come up a few times in our class. It's called a fan disk. It's like a part of a car. I have no idea what it is. In unsupervised learning, there's some really obvious things to be done here in segmentation. And we'll see that exactly the algorithms people use for mesh segmentation are what shows up in unsupervised learning. They're not at all different. It's just that they're described in completely different language. And then finally, of course, in machine learning and graphics, this shows up. So for instance, maybe a big data set of 3D models. One of the kind of holy grails that I think we still really haven't accomplished is I have a big data set of tables and chairs. This isn't fiction, by the way. You can really download a big data set of tables and chairs. And somehow, people have put like a ridiculous amount of time into modeling tables and chairs. Really specifically. I feel like, you know this video clip of Zuckerberg where he keeps saying, what is it, brisket and ribs? Anyway, so I have a big data set of tables and chairs, and now I want to make a new table. How do I do it? Well, I open up AutoCAD, and what's at my disposal? Like a bunch of rectangles. Well, that somehow is not that great, right? Like, I just put all this time into modeling these really complex objects, and now I want to make another object in the same class. Somehow the intuition is that I should be able to reuse some of the work that I just did, right? And so there's some learning task hiding here, which is, if I have a big data set of kind of analogous objects and I want to make a new one, can I sort of learn based on like what does the typical table look like, sort of an intelligent user interface for 3D modeling that takes that into account. Right? And so one of the basic steps in a lot of algorithms that have been proposed for that task, which really aren't adopted in practice, I think they're really not usable at this stage, is to kind of take these things and segment them into pieces. Right? The idea being you take, kind of scissors to these surfaces, and then you make these Franken surfaces that kind of combine aspects of different ones. And in fact, if you look at a lot of these papers, it really is what they propose. They just glue together like the legs from one table onto the surface of another, and that looks about as good as you would expect. By the way, there's one really bizarre, sorry, I should be careful because it was written by a colleague at UMass. There's an interesting paper at SIGGRAPH a couple years ago where they talk about zoomorphic design. Have you guys seen? You should look, it's kind of funny. They propose taking a 3D model of, it's very specific as algorithms go. You take a 3D model of an animal and a 3D model of a piece of furniture, and then you make a piece of furniture that's shaped like this animal. And this is at SIGGRAPH. Yet they reject my work sometimes. No, I'm just teasing. Actually, from an algorithmic standpoint, it's very interesting stuff. But it's really a double take. Okay, so let's say that I'm given a surface, and I want to know, like, what is a good segmentation? Like, how do I know if I succeeded at this task? Any ideas? Ground truth. Yeah, that's probably the obvious one, right? So it matches data that I have. What are the things? Like what defines a good, either in the segmented or the supervised or unsupervised case? What does it even mean if it agrees with the ground truth? Is it IOU? Is it optimal transport? You guys just learned about 2 lectures ago, or last lecture rather. Yeah.
Clusters give you useful similarities.
They give you useful similarities. Yeah. Maybe they have similar geometric property. Yeah.
Also useful differences in that the 2 clusters should have something differentiating.
Yeah, maybe they divide the surface into pieces that are kind of interesting to compare to one another. Connectivity, yeah. Disconnected clusters, probably not a terribly useful one. Actually, my research group studies political redistricting, and that constraint really gets in the way. That's a separate matter. Yeah, maybe separation. Certainly a machine learning case, right? You want kind of well-defined pieces. What was that, Yui? User studies, that's another good one. Yeah, in fact, we'll see an example of that in a bit. Maximizing distribution. In other words, like, yeah, so maybe you want to kind of cover lots of surface area and have a little perimeter or something like that. I'm putting words in your mouth, but they're the ones that I'm looking for. I think the answer to this question is that it is application dependent, and I think we just heard that from all of you guys. In fact, mesh segmentation was like this funny cottage industry in academic geometry for a couple years. And lots of people, including myself, I'm guilty of this. One of my first papers in graduate school was the segmentation algorithm. And it's really not clear that that's an end in itself, right? Like, really that should be plugged into an application, and that really defines what makes for a useful segmentation. And every single answer that you guys gave is completely reasonable, yeah? And so my unsolicited advice is that if you see a paper and it just says like, we have the top performing segmentation algorithm for surface, you really should be suspicious, right? They should be saying segmentation for X, right? Or segmentation which has top performing performance on task Y or whatever, yeah? One way that people have gotten around this in geometry area, in case you have a way to find blobs on a bunny and you want to publish it, is to say that you have a semantic segmentation. I feel like is a phrase you hear a lot in machine learning. In the lecture slides, I think I forgot to upload this. I get all of my lecture material from Facebook, and there's actually a funny rant by a colleague, Aaron Hertzman, who is a computer graphics person turned kind of machine learning guru, who like really strongly is opposed to the use of the word semantic. And I don't disagree with him. For one thing, semantic really is a word that comes from linguistics, and we rarely use it in computer science in the fashion it was intended. But more than that, it's sort of this catch-all for like, I don't know, it makes kind of like blobby stuff that like somehow aligns with what I might expect. So anyway, I'll let you read that offline. That said, there are many attempts to standardize, and this is a great problem where like segmentation for brain imaging or segmentation for computer graphics, those make sense. And in fact, there's a number of benchmarks out there which are super useful, because if you do want to study this kind of problem, you now have some gold standard to measure yourself against. And indeed, there's some really clever techniques out there whose goal is to take sort of a black box piece of code that like takes in an object and gives back a segmentation and tells you how well they're doing for a particular class of problems. Yeah, and it really actually this from Tong Funkhauser's group at Princeton, this benchmark for 3D segmentation, a little bit overlooked these days, and it's a really clever way to sort of release a data set and have people use it in a meaningful fashion, which I think is a little bit of a lost art in this high-speed computer vision world. Okay, so for today, we're going to talk about mostly geometric methods, which of course is not that much of a surprise given the topic of our course. Yeah, but it is important to keep in mind that while we're going to kind of separate off the application a little bit, we should think really critically about which of these are useful for who, and go accordingly. Can anybody name a geometric segmentation technique? I think you all can. All of you have seen segmentation somewhere. What's a clustering algorithm? K-means. K-neighbors I'm not familiar with, but I can guess what that might mean. But certainly the K-means algorithm, I think, is one that we've all seen. And I would argue that this is essentially just a geometric object, right? What is K-means? Well, okay, so you have K-means, which are summarizing your data. And roughly, these are K data points that are intended to summarize a much larger data set. Right? And one of many ways to understand the K-means algorithm, so what do you do in K-means? You have K points. You're trying to summarize a big cloud of points with, like, say here, I guess 3. Yeah? So you assign every point to its closest cluster center. That's the circles here. This diagram's a little hard to read. Right? So like this guy gets assigned here. And then what do? I replace his position with the average of all the guys that got assigned to it, and then I iterate. Yeah? I think this is an algorithm that we're all familiar with. One thing that you might not have realized is that you secretly were solving an optimization problem when you did that. Yeah? In particular, I would say that the optimization problem is over 2 sets of variables. There's a set of means, right? That's like the circles here. And then there's a discrete variable s, which is the assignment of points to means. Right? So one way to understand the k-means thing is that you're minimizing the sum over all k, right? This is like the sum over all your cluster centers. And then here, the sum over all the guys assigned to that cluster center, the distance to this thing. Yeah? So let's think for a second. What would happen if I held mu fixed and I optimized for s? What's the best way to deal with that? Well, this is summed over all of the data points. So to make this thing the smallest, what should I do? To its closest mean, right? It's exactly right. So I should assign every point to the closest mean. And similarly, if I held s fixed and I just optimize over mu, well, this is the least squares problem, but conveniently there's no matrix here. Yeah? I noticed I watched my old course lecture and we derived the formula, but I actually don't think that's a great use of class time. If I optimize for the mu i's, what am I going to get? Just the mean of all the guys that are assigned to it. Yeah? And so the K-means algorithm is nothing more than what we may call alternating optimization, right? First I hold the mu's fixed and optimize for S rather. That just assigns everybody to their closest mean. And then I held man, I'm struggling today. I hold S fixed and I optimize for the mu's, which is just averaging. Yeah? So here's what that looks like, right? So there's an assignment step for S, right? So here the S is the set of X where it's closer to mu than to any of the other mu's. Does this notation make sense? Does anybody know what these partitions are called? The set of all X for which this inequality is true, given a set of mu's? This is the Voronoi cell. You guys see that? Because this is the set of points that are closer to mu I than to any of the other mu j's. That's what this is saying in words. Yeah? So this is the Voronoi cell corresponding to mu I. Which, by the way, you can kind of see in this diagram, right? Like these are Voronoi cells here. Yeah? And then the update step is just averaging, right? Got to remember to divide by the size of your set. Common bug. Okay. So this is really a geometric technique, right? All it's trying to do is minimize distances, and we can poke at the boundary of this thing to come up with other geometric methods for clustering, which are all totally reasonable. Yeah? And really all this corresponds to is locating points so that the Voronoi diagram corresponding to those points somehow resembles the clustering that you see in your data set. Right? That's like a fancy way to put what's going on in K-means. And of course, you can make all kinds of fun videos that show K-means in action here. I managed to find one on YouTube, which is not loading. Come on. For some reason, the YouTube plugin in PowerPoint makes you go a slide forward and then back. Yeah, so here's a bunch of data points, and here's the K-means algorithm in action for the lines of the assignment to the centroids, and then you can see they're kind of moving around as it updates. What are some drawbacks of this technique? Yeah. Absolutely. This is an extremely non-convex optimization problem. In fact, the way I've written it here, it's got discrete variables in it. Yeah? So there's no reason why this alternation back and forth between S and mu has to converge to the global optimum. In fact, it typically does not. Yeah? And so K-means is famously prone to local optima. Essentially what you see in this technique is often basically some small modification of your initial guess. Yeah? What that means is that there's a big science out there in terms of choosing clever initial guesses for K-means. We're not going to cover them in this class because they're either heuristic or they require a little bit more probability than I'm assuming in this course. There's one that's worth reading about called K-means++, which is extremely simple to implement. You know, this was a thing historically. You put ++ at the end of the name of a paper to kind of indicate that you were the next guy. Right, and then later on, like when iPhones were a thing, we had like K-means probably at some point. And, you know, now I guess we would have what, K-means flow or something. But in any event, you know, there are a lot of different applications. A very simple one might be you take, you know, maybe I want to compress a photograph. You know, and one way to compress photo would be reduce the number of colors in the photo, because then somehow I need fewer bits per pixel to do that. Yeah, so I could take the big point cloud, which is all the RGBs I see in the photograph, run K-means, and then what I get is some kind of Andy Warhol-looking approximation of the photograph that I have. Probably I would take K to be a power of 2 in practice. Yeah, but of course, like storing, 16 bits worth of information per pixel is a heck of a lot less than RGB as 3 different double precision floating point. And indeed, a lot of the early image compression kind of formats really leverage this trick. The idea being that I can store a color palette, and then I can store indices into that. And so, for example, if I take a photo of the sky, then I probably want more blue in my palette than in this classroom, which is more kind of greenish and brownish. Just FYI. And yeah, so that's what it allows you to do instead of just quantizing color. That makes sense? Of course, if you wanted to segment a mesh, you now have a technique for doing it, right? Because remember that we just spent the last 4 or 5 lectures coming up with all kinds of clever descriptors for vertices on a surface. One very simple thing you could do would be compute, here's the GPS, you could compute the heat kernel signature, any of your favorite signatures, and just do K-means clustering on them, and you'll get a reasonable partition of your surface. Question, does that guarantee, if I do K-means, does that guarantee that my surface is cut into K pieces? No, right? There's no reason why that Voronoi diagram in heat kernel signature space has to correspond to contiguous parts of an object, right? And so you could have very bad luck. So for instance, maybe your heat kernel signature space for some reason looks like the letter Y, and one of your Voronoi cells looks like that. You had really bad luck, right? Like this is the two arms and the feet. Then these two hands are part of a cluster, but they're not part of contiguous parts of a surface. But somehow what people have observed over the years, that's pretty rare to happen. When do you think it would happen, by the way?
Extremely symmetric objects.
What was that?
Extremely symmetric objects.
So yeah, in fact, my bet is that this armadillo here, to repeat Colton's answer, was symmetric objects, right? Because remember, in heat kernel space, or in GPS space, right? What happens to the two hands of this armadillo? They get squashed together, right? They look the same. So probably this technique actually clustered those two guys, and my bet is that K is smaller than the number of segments that you're seeing on the surface here. Yeah. I don't know, I'll have to ask Raif. Of course, the dependence on an initial guess, I treat it kind of like a bug. Other people have thought of it as a clever feature. So in 2008, a very popular technique for mesh segmentation was proposed you'll see in each of these lectures, I think you end up seeing the same name over and over again, because each lecture kind of corresponds to one person's career a little bit. So last time was de Goesch, now we're going to do Funkhauser. Right, so one of the things that Tom proposed, he's now at Google, was to just keep randomly, K-means, yeah, it's initialization dependent, so maybe what I do is I just run it 1,000 times, I get 1,000 different cuts of my mesh, and then I try to say that a good segmentation is somehow one that has edges that tend to appear more often when I do that, right? So for every edge of my mesh, I just count the number of times that it was cut, and they tend to get a pretty nice segmentation this way. This is kind of a clever trick. And indeed, that sort of alleviates your dependence on initial guess, because in some sense they're computing an expectation now under Kmeans algorithm. Makes sense? This is kind of a clever trick. Incidentally, one really critical issue with K-means is the number K. So if we talk about unsupervised machine learning, I think this is really one of the big downfalls. I mean, I already whined to you guys about the fact that when we do manifold learning, you need to know the dimension of your manifold, and that makes no sense at all. There's sort of a similar issue here, which is if I knew the number of clusters in my data set, then obviously I know more than I am letting on when I do my analysis, right? If I'm truly doing some kind of exploratory data thing, it's pretty rare to have a really clean cut into K pieces, and to make matters worse, because K-means is initialization dependent, it could be I have a really nice cut into K pieces, but I just don't see it because I got bad luck when I ran. Yeah. There's a really beautiful research paper which was in the early 2000s here from Tib Shirani and I don't know the second guy, Walther and Hasty. At least the first and the third are famous. I'm sure the second one has had a distinguished career too, but I don't happen to know who they are. And essentially, they're trying to answer this question of how to choose K and K-means. How many of you guys have seen this paper? It used to be popular. Yeah. It's kind of interesting stuff. So essentially what they propose is a technique where I make a plot that, remember that K-means is an optimization algorithm, right? It optimizes that functional I gave you before. So what they do is they make a plot where the horizontal axis is K, and the vertical axis is that objective value, right? If you're lucky, that decreases. It typically does. I think it's pretty rare for it not to. Certainly if you get the same initial guess each time, it will. And what they sort of observe is that there's often what they call kind of a knee in this plot, like an area of kind of high second derivative, where after which it kind of flattens out. And they propose, they're statisticians, so of course they need to propose a summary statistic, and in this case they have this thing that they call the gap statistic, which essentially measures sort of the vertical change in this object. And they say that sort of a good choice of K, roughly here-ish, is where the slope of this line starts to flatten out. I think that makes a lot of sense. So this is to my knowledge, the most systematic sort of treatment of choosing K and K-means, and it's worth a read. It's not so hard to look at. Some clever stuff. And they, in fact, of course, they're statisticians, so they have some kind of null hypothesis style test to kind of check whether or not the K is the right K. Incidentally, one kind of interesting issue that can come up in Kmeans is that there's no control over the size of the cell. Right? So it could be that one of your means is assigned like 2 points and another mean is assigned 200 points. And for many applications, that's really undesirable. How do you think we might solve that problem? What was that? Sure, it's some kind of regularizer that wants to regularize the size of the Voronoi cell. Can you think of one? Can we think of a theory that was covered in the last couple lectures that has to do with areas of things? You're killing me. You're killing him. Oh, wait, I got time. Control theory? Who the heck? No, Earth move resistance. Yeah, no, yeah, optimal transport is a great solution to this. In particular, let's actually return to it for just a minute here. And since Sebastian gave a stellar lecture, you guys should all be able to parse what we'll talk about for just a minute here. So remember an optimal transport story. You guys didn't cover this, right? I looked at the slides. I don't think you did. Yeah, just very briefly. So remember in transport, you're given two distributions. You want to find a map from one into the other. Yeah? And let's say that I put an additional ansatz on one of the two distributions. I assume that it's composed of a finite number of points. So this is like delta functions if you're an electrical engineer. Yeah? So I have one distribution which is concentrated on a few points, and the other one I can't say anything about. It's some smooth thing. It might be a Gaussian. Yeah? Then one of the kind of interesting takeaways in optimal transport theory, so remember that when both of them are a bunch of delta functions, we can solve this problem using a linear program, right? That's what's on your homework. So you're all experts on it now, right? There's that Tij, and there's a -1 that you guys don't like. That's in Sebastian's slides. Okay. I read Piot, so I'm just too lazy to respond. Okay, so right. So in any event, okay, so in that case you can solve with a linear program, and essentially one way you could kind of understand that is just asking the question of like, when can I solve the optimal transport problem with a finite number of variables, right? Because if I did transport between two Gaussians, I need to move like every point on the plane to some destination, and that's more variables than my computer can store, right? But if both of them are a bunch of deltas, then you can solve it because there's a finite number of unknowns. But there's a second case where there's a finite number of unknowns. And that's the one that I've shown here. This is called semi-discrete transport. So here, one of your distributions is composed of a finite number of points, and the other one ain't. It's just some smooth object. But here's the little lemma that you can convince yourself, is that there's never a case when you want to leapfrog. Okay? So remember the transport problem, right? It says I've got a pile of sand here, and I have to distribute it over the blue guy. Yeah? And there's a lot of different choices, right? I could move it like over here somewhere, I could move it closer. And there's this object called the transport plan, which tells you like for every point where its source came from. Does the story sound familiar? Sebastian's a much better lecturer than I am, so I'm sure that it did. Yeah, okay, so in any event, the thing that you can convince yourself is that if this guy is to the left of this guy in one dimension, then all of the mass to this guy in the target distribution ends up to the left of all of the mass to the next guy. In other words, there's never a reason to do that in your transport plan. I think that's intuitive. Yep. What does that imply about your optimization problem? Is there really an infinite number of variables? Do I need to know for every single blue guy where it came from? No, I just need to know sort of the leftmost and rightmost point and say this entire region went to that first guy, this entire region went to that second guy, and so on. Yeah, so there's actually secretly hiding in this problem a finite number of unknowns. This is called the semi-discrete transport problem. Yeah? So this picture is very clean. It does lift to higher dimensions, and it makes for a really beautiful image and totally uninterpretable. It looks something like this. But the basic idea is you get an object which looks kind of like the Voronoi diagram, but the difference is you need to be able to control the size of your cell. So the way that you do that is you introduce a new object called a power diagram. I actually don't know why they use the word power here. I should. It goes back to the computational geometry community, like the meshing, Delaunay, Voronoi people. But in any event, you take your Kmeans, or your points here, and you're going to attach a second number to that point, which is a bias to the distance function. So now I'm going to say, rather than thinking about distance to point I, I'm going to think about distance to point I minus some second number, which is phi I. I'm going to define the Laguerre cell corresponding to a point xi. So if this phi weren't here, notice that it's just the Voronoi definition we had before. If c is distance. But now I'm going to like subtract a number. So what happens if phi is really big? What happens to the size of the cell? So phi is big and positive. So this number on the left-hand side is small. So the cell effectively gets larger, right? There's more points where this is a small number. Yeah? And so in the semi-discrete transport problem, what you do is you have explicit control over the size of each of your Voronoi cells, which is provided by these phi's. And the name of the game is to kind of find a choice of phi that balances out the size of your cell. So in some sense, yet another way to just to kind of understand what Sebastian talked about in your last lecture is nothing more than some kind of version of Kmeans where you have some control over the size of your Voronoi cell. That's it. And so this is useful for a lot of things. For instance, to highlight your TA's research a little bit, there's some interesting questions involving kind of machine learning style problems where maybe you don't actually have access to your data set, you just have a sampler, right? In which case, well, you sort of have a semi-discrete looking picture because you just have the discrete set of samples from one distribution or another. And this is the kind of machinery you can use to approximate transport distances or even summarize all that good stuff. So I think I'll let you look in the slides for details there. But for now, I think it's time to take a nano quiz. Is that right? Cool. So I'm going to update my GitHub really quickly, and hopefully it's in there. You should commit. Gotta commit. So everybody pull out their laptops, their scrap sheet of paper here. My apologies for doing it at the end of lecture today. These things happen. They shouldn't, but you have a terrible instructor. Don't say that in your reviews, though. I'm up for, tenure reviews. Okay, no, just kidding. You should be on. Are we good? So I do big money, no whammies. Only one forgotten nano quiz is better than the last time I taught this course. Yeah. Okay. Already up to date. Huh? What was that? Yeah. Now you're good? Sorry, guys. I know this is what... Nope, still not there. I'm just going to keep doing it. Is it, though? Okay. And can we turn off the camera, by the way? We don't need to put our quiz online. Okay, fab.